All right. Hello, everyone. Welcome to the next session. I would like to introduce, we're starting a few minutes late, but hopefully we'll catch up. I would like to introduce Stella Katsarou. Stella is a member of Peltarion AI research team, and she's a recent graduate of the ML Master's program at KTH. So her thesis focused on improving multilingual language model for low resource languages and measuring gender bias in contextualized embeddings. So, and today, in fact, we're gonna, I think, hear a little bit about bias detection in transformer model representations, right?
Right, Galina.
Yeah.
And
so we're looking forward to this. Just a quick reminder that there's a little Q&A where you guys can ask questions throughout this. The talk will be about 25 minutes, and there will be 5 minutes of questions. Thank you.
Nice. Great. So good morning, everyone, and thank you so much for having me here. It is fantastic to be part of such an inspiring conference as this one, and thank you, Galina, for the lovely introduction. So yes, today I'm going to be talking about quantifying gender bias in the contextualized embeddings of transformer models. And since this was part of a thesis project conducted in collaboration with KTH and Peltarion, you can also see the names of the people who supervised it being mentioned in that slide, namely Andres Arteg and Borja Rodriguez Galvez. But let's inspect the title once more, and let's just go through the words one by one there and make sure that everyone feels familiar with the vocabulary being used in the title. So embeddings. What is an embedding? An embedding is a numeric vector that we use in order to represent a word. In that case, we use this vector to represent the word happiness, as you can see in that slide. Why do we need word embeddings for? So usually we use them as inputs to a machine learning or deep learning pipeline of some sort. And they can also encode meaning in such a way that semantically similar words are closer in the vector space. And focusing a little bit more on the last phrase here and making sure that we, visualizing it so that we can actually understand it better. Let's say that we somehow reduce the previous embedding that was a huge one with dimensionality of 200 to a dimensionality of 3. We somehow reduce the dimensionality of our embedding for the word happiness. And we do that so that it is feasible for us to visualize it as a point using the 3-dimensional plane coordinate. And then I'm going to repeat the definition once again. So word embeddings can encode meaning in such a way so that words which are semantically similar, as is the case with the word cheerfulness and happiness, are represented in such a way so that they are then close in the embedding space, as you can see in the visualization on the right-hand side of that slide. So now that we have an understanding of what an embedding is, let's move on to the next word, which is contextualize. So what that means. So we have two types of embeddings. We have non-contextualized embeddings and we have contextualized embeddings. Non-contextualized embeddings are fixed. So once you train the model or use the algorithm that you use to produce them, they are frozen. They cannot really change. So each word has a unique vector that is associated to it. But that's not the case with contextualized embeddings because they can also take into account the surroundings of a word. In other words, they are of mutable nature. They can change. And using a visual example, say, for example, that I have the word bark. That can be the bark of a tree, but it can also be the bark of a dog. For non-contextualized embeddings, I am going to have the same vector for both words. So non-contextualized embeddings cannot account for polysemy, and that is a very large drawback for those, but that is not the case for contextualized embeddings. For contextualized embeddings, I'm going to be having different embeddings for both words, even though they sound the same, it's a different meaning, and that can be captured by contextualized embeddings. And how they do that is that they take into account the surroundings of a word inside a sentence. For example, here, he burnt the tree. If it's bark, we can understand that it's a tree bark, and then why do dogs bark? We can understand that it's a dog bark. And of course, contextualized embeddings are being used by transformer models. Excuse me. And transformer models is the main deep learning algorithm that we use today in natural language processing. It's widely being used for NLP use cases. So now that we also understand what contextualized embeddings are, let's just focus on the whole thing, gender bias in contextualized embedding. And here we can see, let's go back to our visualization from before, and we can see cheerfulness being close to happiness, and then again we can see other words that can be close semantically, for example, lunch and sandwich being close together. And that is expected. This is normal behavior, but this one is not. So you can see on the right side, man being closer to programmer, but then programmer being far away from woman, which at the same time happens to be close to homemaker. And one reason that can be happening is because we have bias, gender bias in this case that was present in the corpus that we used to train. And what we are doing here is essentially that we are visualizing a gender bias incident. So if bias is present in the training data, then we do have a problem, because that is the data that we're going to be using to pre-train our NLP models on. And then these kinds of behaviors are going to be reflected in the downstream tasks in the models that we use in production for everyday life use cases. In other words, if we have bias in, then we are going to have bias out. And as an example, I'm going to provide the Amazon recruiting system. So a few years ago, Amazon wanted to automate its recruiting process, so they created a model to do so. But eventually that model ended up downgrading resumes that included the word women's, for example, phrases like women's basketball team and the like. And that presumably happened because the model that they used tended to associate women less with the job occupations, with the occupations that they were looking to hire people for. So yes, quantifying those gender biases is important. And why is it important? Because of course, we can only reduce something that we can measure first. And that is the objective. That was the objective of that study. So how did people do it before? Bias detection can be done in different ways, but it always depends on whether you're dealing with non-contextualized or contextualized embeddings. When it comes to non-contextualized embeddings, then you can have analogy tests or association tests. Analogy test is when you provide a pair of words that are close, for example, man and king, then you provide a third one like woman, and you can expect to have another word generated by the model, for example, in this case, queen. And that would be an okay example, but not the next one. Man is to doctor what woman is to nurse. We can see some sort of gender-directed prejudice being encoded in that one. Association tests is the difference between differences of a word and a good attribute and a word and a bad attribute. And if the model is unbiased, we can expect those differences to be equal or similar. Moving on to contextualized embeddings. So given that models like transformer models, for example, have been present 2017 onwards, this also is a relatively young field, bias detection and debiasing in transformer models. And here we can see some of the studies being conducted in the past. I'm not going to elaborate on all of them, but let's just take a look at the cross pairs, the one that you can see on the right-hand side of this slide. So we always have in that case pairs of sentences which are being repeated. We have the same sentence, the only thing that changes is one word. So essentially what we have is a modified part of that sentence, in that case fat and thin, and then we have an unmodified part of the sentence, which is the one that is being repeated. And yes, I apologize for the content of the examples being mentioned here. It's just that we need to use them in order to trigger biases by the model. And what we want to compute in that example is the probability of the unmodified part of the sentence given the modified part of the sentence, and theta, of course, the model parameters. And in the other one on the left side, stereo set, we compute the opposite, the probability of the modified one given the unmodified and the model parameters. In any case, what we want to compute is the preference of the model towards stereotypical behavior. But let's see how we did it, right? So how did we measure stereotypical biases with respect to gender in contextualized embeddings? So this is our research question. How can stereotypical biases be detected and measured in the contextualized representations of T5 and MT5? T5 is a transformer model, an encoder-decoder transformer model, and MT5, which stands for multilingual T5, is its multilingual variant. So this was our approach. As a first step, we created a dataset so that we have something to work with, and then we detected bias using two ways. The one is on a downstream task, the task of semantic text similarity, the first one. And the second one, which is mentioned as step 3 here, is to measure bias directly on the contextualized embeddings of the transformers that we studied. But let's focus on the first one to see how we created our data set. And this is what we can see here. So we started from a raw data frame. We use the STS benchmark, and that you can find a lot of sentences in there, which is what we wanted. And you can see some of them being visualized here. For example, a girl is styling her hair, and some other ones as an indication. What we did next was that we only kept the sentences which start with a man or a woman, and we would discard the rest, as you can see in the middle of this slide. And then out of the ones which started with a man or a woman, we would also discard those which included pronouns. We did that because we only wanted gender information to be disclosed by the subject of a sentence and not by any other word present in the sentence. Then we proceeded with counterfactual data augmentation, which is essentially that we use the same sentence, but every time we replace the subject with a different word. For example, he is playing a harp. This is the second row on the bottom of the slide. He is playing a harp, she is playing a harp, a nurse is playing a harp. So we would every time replace the subject, ending up with 52 columns because we're using he, she, and 50 different occupations. In that slide, you can only see the nurse occupation as an example. And that is the final data frame that we worked with. Moving on to the second step, which is the first method that we use to detect gender bias. So we worked on a downstream task. The downstream task that we worked with is called Semantic Text Similarity, and the dataset is called STS benchmark. And that is a parallel dataset, meaning that it's both available in English and in Swedish, which came handy for us because we were able to do experimentation both in Swedish and in English, and we were able to do comparisons. And let's see how the dataset looks like. Every example consists of 2 sentences, and then the target is a float that denotes the extent to which those are semantically similar or not. For example, an airplane is taking off, a plane is taking off. Those are very close semantically, so they are assigned to a high score. Scores can vary between 0 and 5. So this one is assigned to 4.7. And then we have the other example being there, and then we have a woman is walking, a man is cooking. those are very relevant semantically, so the score that they are assigned to is close to 0, it's 0.6. We used MT5 for this suite of experiments, the small base and large version for it, and what we did was we fine-tuned the model on that data set, and we then later used MT5 in inference mode, which means that we would feed a pair of sentences to MT5 and we would ask it to give a similarity score for that pair of sentences to us, as this was the task that it had learned to do at that point. And this is the core of this method. This is exactly what we did. So let's focus on that table over there. We have a source sentence, for example, a nurse is walking. So the occupation that we're studying is nurse. And what we do is we create pairs of sentences. One for the male and one for the female gender. A man is walking, a nurse is walking. One for the male gender. We feed that to MT5. MT5 outputs a similarity score. Since we have 150 sentences in our data set, we have a mean similarity score, of course. And then we do the same for the female gender. A woman is walking, a nurse is walking. Feed that to MT5, get a mean similarity score for our data set back. And if the model is unbiased, we can expect those two similarity scores to be the same, but that was not the case, as you may have guessed by now. So in that case, MT5 obviously associates women more to nurse than it does to the male gender. In that graph here, you can see similarity scores on the x-axis and model sizes on the y-axis. And then on the bars, you can see the similarity scores for the male and female gender. You can see two things. You can see that the differences are getting larger and larger the larger the model gets, and that the biases are not present for the small version of MT5. In that slide, you can see a comparison between the English and the Swedish language for all 50 occupations. The previous one was only focused on the nurse occupation, so here we have all occupations. And as you can see, the differences are less important for the Swedish language. We can see larger differences for the English language instead. And here we focus again, once again, on the nurse occupation, and it's yet another comparison between the English top and then Swedish on the bottom language. And you can see comparisons between the different sizes of the models, and you can also see the differences growing larger as we work with larger models again. But again, the differences are smaller for the Swedish language, as you can see at the bottom of this slide, and they might as well be statistically insignificant. And then, yes, let's move on to the third one, the third step, which is the second method that we used to detect bias and contextualize embeddings. So to do that, we used T5, which is a monolingual model available in English only. And here you can see our data set once again. So here is what we did. Let's focus on the first column. He's playing a harp, he's cutting onions. So we take all those sentences and we feed those to T5. And then we extract the embeddings for the word he. And those are contextual embeddings. So we end up having 150 different he embeddings. And then we also have 150 different she embeddings. And those two we use to produce G, which is our gender direction in the embedding space. So the gender direction, how we compute it, is mainly the mean. It's just the difference, the Euclidean distance between he and she, the mean value for it. In order to make sure that we compute it in a robust way, except for Euclidean distances, we also compute angles between the 150 different he and she embeddings, and we find that there is an angle, a mean angle of 0.68, plus minus 0.04 radians. So that indicates that we have a robust computation of gender direction. Then we do the same for the occupation that we are studying, focusing on the third column in our data set here. We can see that, yes, so we feed that to T5, and then we get 150 different embeddings for NERs. And let's now focus on the formula, which is BI equals 2. That's our metric. That is called gender polarity. Gender polarity is a metric that measures whether a word is more polarized towards the female or male gender. And W is the embedding for the nurse occupation here. G is the gender direction that we just computed on the left. And this is actually nothing more than like a projection on the gender direction, because as you can see, it's the inner product between the vectors divided by the product of their norms. So it's simple, yet powerful. And if we had fixed embeddings, if we had non-contextualized embeddings, we would only have one value for gender polarity. But now that we're working with contextualized embeddings 45, we end up having 150 occupations for every word. Thus, we end up having 150 different B values. And that is what? That can be a distribution. So we visualized that and see in order to see how that distribution looks like. And that is what we will see in the next slide here. So on the left, you can see the she distribution with orange color. And then on the right, you can see with blue color, the he distribution. So those are our two extremes. So those are our two gender polarity distributions for the two genders. In between, you can see the distributions for the different occupations. And you can see that the nurse occupation is the one that is closest to she distribution. And then you can also see that the programmer distribution is closer to the one that regards the male gender. And that we can see on the top of the slide. If we focus on the other graph that is on the bottom of the slide, you can see that the distributions are traveling towards the two extremes, closer towards the two extremes. So we can see occupations like homemaker, receptionist, or nurse being closer to the she distribution, and other distributions like associated to higher status occupations like programmer, engineer, surgeon being closer to the he distribution. So we can see gender bias being visualized in those graphs. And this is for T5, a model that we might as well use in production for our applications. So moving on to the conclusions, we quantified gender bias using two ways. One of them was the one that we just talked about on the embeddings directly using gender polarity, and then the other one was on a downstream task. And both yielded the same results. Then we also saw that the Swedish language might carry less biases with respect to gender stereotypes than the English one. But we also noticed that biases emerge for the large base and base T5 and MT5, but they subside for the small version for specific occupations. If you're curious to reproduce any of the experiments, this is a repository in order to do that. And the last slide here is about debiasing, which should come naturally as the next step. I just, as a reference indicatively, I just mentioned some debiasing methods for non-contextualized embeddings that have been around, like hard debiasing, linear debiasing, or partial debiasing. But of course, that can be different for contextualized embeddings, and this is something that we now do continued research at Peltarion together with KTH and TRICE. And with that, I would like to end that presentation and thank you all for your attention, and I'm happy to take any questions.
Thank you very much, Stella. It's really appreciated. It was a very interesting topic. I've been digging a little bit into NLP lately also, so a lot of interesting questions pop up. But I will start with Q&A that we have from our audience. So Asli is asking, do you know of any study that looks into biases in gender-neutral languages where they don't necessarily start the sentences with he or she? And if yes, is it still a problem in those languages?
So that is a great question to begin with. Yes, I've seen papers that include languages like that in their experiments. I do not remember the titles of the papers by heart, but I could reach out to you later and discuss about it. If it is still a problem in those languages, it shouldn't be, but I do not remember the results, to be honest. But one thing that I do remember regarding this example is that even if it is not for those languages, and say that we use languages like those and translate them back to English, then the biases are going to magically reappear. And every one of us could do a little experiment to find out. Just go to Google Translate and put a sentence using one of those languages, and yes, choose to translate it into English and see which pronoun, female or male associated one, pops up for specific occupations. But I would say that even if it's not present, it's probably because it's being covered, not because it's not really there.
Thank you. And now we have a question from Amir. As T5 is a generative model, if needed to generate a sentence as an output for a downstream task, it generates two sentences, i.e. one for female and one for male in your model. Is it correct?
Yes, thank you for that question. So, correct, T5 is a generative model, and it's a very special generative model in the sense that, and that is the novelty about that model, you must always have text as input and text as output. That text can be anything. In our case, the input was pairs of sentences and the output was a floating point, but again, expressed as it was a string. So it was a string 3.5, for example. So we would have two different inferences, one for the female pair and then the score, and then one for the male pair and then again the score.
Okay, thank you very much. And now we have a question from Anna Katarina. Do you think you would observe similar biases in languages where occupations have different endings depending on the gender? Because I'm sure there's bias, just wondering if you would also find it that way.
Yes, I'm confident that we would, and this is something that we would also like to include in the research that we're going to be doing now. But yes, definitely, I think we would,
Okay.
and even more bolder gender bias incidents.
Stella, thank you very much. This was really interesting, and we really appreciate you sharing this with us.